Should get the message that we're recording. So Ochir actually misses Saga and having to cook his own food. But he's trying to stay sane, and his living arrangements are a little different because he wasn't able to go home, which is unfortunate. All right, so I should be sharing my administrative slides, and I am going to get started. So is Ian on the line? Let's see. You ready to take over? You ready to take over with your presentation?
Yeah. Am I clearly audible? I'm using an external monitor. My laptop's closed. I don't know where the microphone is on it.
Yes, I can hear you fine, Ian.
Okay, good. Okay. Where do I take control? Share? How do I take control?
It's the little box with an up arrow. If you click on that, it'll give you the option to share either your screen or an application.
Oh, okay. Okay, is everybody seeing that?
Yep, I see it.
Yeah, I can see it.
Okay, cool. Okay, good. All right. Yeah, this is weird and different. Okay. All right, so I'm doing a presentation on SUSE Linux. It's a little tricky. There's like several different implementations of SUSE Linux, but we'll get to that. Arrow keys. Hello, where are you? There we go. For devotional today, I did Matthew 6. I was in my dining room the other day and just kind of looked out the window, and there was a little house wren. It was out on the patio, and I don't know, maybe I was too tired and I was like thinking deeply about things, I don't know. But I was like, that's kind of interesting, just with everything that's going on. This verse came to mind about, how everyone's very concerned, and rightly so, about getting jobs and, financial security and what have you. But the reality is that God is taking care of the birds. How much more will He take care of us? Therefore I tell you, do not worry about your life, what you will eat or drink, or about your body, what you will wear. Is not life more than food, and the body more than clothes? Look at the birds of the air. They do not sow or reap or stow away in barns, and yet your heavenly Father feeds them. Are you not much more valuable than they? So that verse just kind of came to mind yesterday, and I decided to put that in here for my devotional. But yeah, even in the midst of coronavirus, God's still looking out for each of us individually. Should I? Is praying something I should do? Do we do that?
It's totally up to you, Ian.
Okay. Sure. I can't just say that and then not do it, so I guess I will. Okay. Dear God, thank you for this day, this opportunity to share with our classmates something we've learned about different Linux or different operating systems. I pray that we'll glean something from it, and that we'll be able to continue to learn even in this semi-awkward foreign classroom environment. Okay, so let's just dive right in here. So we've got OpenSUSE. Was started by a German software company in 1992. SUSE is actually an acronym standing for Software und Systementwicklung. So that's where that comes from. The operating system was first released in 1994. The company changed hands a whole bunch of times as far as ownership, and one of those times in 2005, I believe in 2004, it was purchased by Novell, and they were big on open source projects. And so in 2005, they founded the OpenSUSE project, which might be what y'all are most familiar with because it doesn't cost money to play with. Incidentally, also, surrounding the controversy about how to say SUSE, I looked up the pronunciation, and if Wikipedia has any say in this matter, the pronunciation is Sousa on Wikipedia, which is like an amalgamation of most people like to say Susie or Sousa. So, I don't know. I don't really care. Say whatever you want. We all get the idea, but that was just, it's kind of funny that it was like at the halfway. So the OpenSUSE project was founded in 2005, and then in 2006, OpenSUSE, or rather SUSE, came to an agreement with Microsoft about interoperability. This was kind of viewed as like a deal with the devil in a lot of Linux communities, just because Microsoft, they'd been through that whole 90s purge of any, where they tried to basically get exclusive domain over the operating systems market. So it wasn't a popular deal, but it definitely solidified their place as a valid operating system. And most recently in 2019, they had another sale, which means that now that they're an independent company and they do all their own stuff. Something that was kind of weird and interesting when I was researching was that they've changed bases several times throughout the development history. When it started out, it was Slackware based, and then briefly it was Jurix based, and I wasn't even familiar with Jurix, but it was just another base that they used for a short time there. And then from 1998 to present, it's just considered Unix-like, and they build their own kernel, and we'll get to that later. But just interesting that they had 3 different bases throughout their history. So this is what I referenced earlier about there's a whole bunch of distributions in in SUSE, because they are both open source and closed source. Like you have to purchase it. So there's SUSE Linux. There's a child running across. Okay, sorry, someone's trespassing on my property. I got distracted there. I'm sorry. Doesn't usually. You don't have children running across your front yard in the classroom. My apologies. Let's see. SUSE Linux Enterprise. So there's the version you have to purchase, which is SUSE Linux Enterprise, and that's the one that gets rolled out in corporations. There are two different primary versions, I should say. SUSE Linux Enterprise Desktop and Server. You can see the acronyms there, SLED and SLES. Additionally, there is SUSE Linux Enterprise for ARM and for embedded systems, which are not as common, but I thought it was pretty cool that they had SUSE especially for embedded systems. That's pretty neat. And yeah, those are the major implementations there, or distributions rather. And then as far as open source, you have OpenSUSE has 2 different kind of streams, and those are Tumbleweed and Leap. Tumbleweed is more kind of end user oriented. It's a rolling release, and it's less server based as opposed to Leap, which is definitely server oriented and is a fixed point release. And you can see there also there's a list of desktop environments that it comes in. Kind of sad it doesn't come in Mate. I'm sure you can make it work in Mate. Mate's my favorite. So here's a very interesting thing when I was looking at this operating system is that the kernel is monolithic, meaning that everything that the operating system does is performed on the kernel level. And I stole this image from Wikipedia about monolithic kernels, but just to give you a good visual representation. We can see here, for example, on the far right, if you look, there's a gray box. Can I use my mouse? I can. I don't know if y'all can see that, but over on the far right, you see device driver. So whenever you put in a device that the operating system is manipulating, the driver is loaded as a module on the kernel level. Obviously, any applications that are interacting with that device or any device are occurring above on the user level. but anything that the operating system is controlling is entirely done on the kernel level, which was interesting. Oh shoot, I had a note here about. This is such a hodgepodge for presentation. Okay, so moving on to functionality. These are some of the popular tools that are in OpenSUSE/SUSE. YAST is a highly commended. Like in my research about functionality, everyone loves YAST. The SUSE website, I quoted their description of it, which is the best/only comprehensive Linux system configuration and installation tool. And from what I found, it does do basically everything. It's like the control panel in Windows, but like 20 times better. It manages partitioning, system configuration, RPM package management, updates, firewall configuration, network configuration, like literally anything that you need to adjust can be done in YAST, which is pretty cool. And seems to be a recurring theme where like there's this centralized, super useful, super powerful functionality within the SUSE distribution. Secondly, another popular thing is open build services, which is, there's a specific aspect of this that's for SUSE where you can supply it with source code and it builds and distributes, or builds and makes packages available for distribution for SUSE operating system. And then lastly, and most interestingly to me, frankly, is Kiwi NG, which the NG stands for Next Generation, I remember correctly. This builds configurable, ready-to-run images of the operating system, which is super interesting to me because that's a lot of what I do or have done historically at work, is system deployment. Basically, this tool does all the work of Windows Deployment Toolkit, Windows Deployment Services, Windows Assessment and Deployment Toolkit, and the pre-installation environment builder all in one. You can make packages that you, or images that you install via a disk. You can make images that you install via network or Pixie Boot, I should say. In pre-installation environment, you name it, you can modify your image in order to have it be installed in that way. So that was pretty cool. Yeah, so those are some of the major functions of SUSE, and I believe that's all I have. Yeah, I forgot to mention earlier that the SUSE OpenSUSE, sorry, not SUSE, the SUSE Linux Enterprise versions are actually like so well recognized that you can actually get from HP and MSI, you can get pre-installed SUSE Linux Enterprise desktop. I thought that was pretty cool too. I mean, you could always do it yourself, but usually you're limited to Microsoft and maybe like Red Hat if you have a nerdy computer company. But yeah, so those are kind of the background and some of the major functionality of OpenSUSE. Any questions? I know that was like a really jank presentation, and I'm sorry. Yeah. What does the name mean? I think I covered that. Software and what was it? Systemsentwicklung? What is your favorite desktop environment? I said Mate. Yeah. Okay. Is there anybody else have anything to add? Questions, comments, criticisms? Can everyone still hear me? Software and system
Yes.
what? Oh, Software und System. I said it in my presentation. Software und Systementwicklung, which means my high school German.
Yeah. My non-existent German.
Software und System. I definitely meant to take a note on what that meant, so that I could translate it in class, but I kind of forgot. I think it's like something to do with configure. I can't remember off the top of my head. I'm sorry. I'm actually.
Don't worry about it, Ian. We can always Google it.
Development.
I'm sure.
Yep. Development.
Oh,
sorry.
Okay.
Yeah, Entwicklung is development. Software and systems development.
Okay. All right. Well, thank you very much.
Okay.
And we see the clapping emojis popping up. So I'm going to go ahead and retake control of the screen. Okay. And Ian, I noticed that your microphone's still on, just in case, just make sure you know.
Oh, yeah. Thank you.
Just in case you had to chase red kids off your lawn or something like that. You know, we wouldn't want to have you hear, "Kids, get off my lawn."
Yeah, sorry about that. The neighbors have a.
Oh, that's all right.
We have new neighbors and they're interesting.
Yeah, I just trying to be humorous there. That's fine. So in terms of presentation, it's the History of Unix team next, and that's Daniel Jones, Hyu-Soo Kim, and Darcini Mohan. And drum roll, please. The next group is the Ubuntu folks, Jason Eaton and Bailey Livingston. So that's what we have coming up. This is the list of assignments that I see coming up. Midnight tonight is the Chapter 5 programming project. I actually have gotten quite a few of those already. So yeah, please get that in. And then Wednesday, April 8th is a Chapter 5 process synchronization quiz. And then April 15th is the quiz Chapter 6 on CPU scheduling. Please take them as early as you can because I'm looking and seeing that we'll probably have a lot of quizzes in mass succession. And as we wrap up, and I know that a lot of you are getting a lot of things as we get closer and closer to the end of the semester. So I would say the earlier that you could take on some of these quizzes, the better off you will be, so we don't give you a mad rush at the end. And then again, April 27th is the Chapter 10 mass storage programming problem, which is, if I remember right, is some pretty easy points. And then Chapter 12 is the optional, May 4th is the optional Chapter 12 programming exercise. That's optional, and it's 10 points worth of extra credit. So any questions about the things coming up or the class in general? So bringing up the slide, and this time I'm going to try to remember to present it. Okay, looks like I have it up. So we looked at various page table schemes because the page table can get large and the search through the page table become a problem, as well as possibly storage issues. So the hash table is another approach. We discussed it briefly. It's useful when the address space is sparse. Otherwise, in other words, there aren't a lot of pages, so that you can then tie into the linked list of elements. It's basically the same advantage as you would have with any hash page table data structure. So the benefits are basically the same, just using that data structure for page tables with all the same benefits. Again, remember that it's most useful for sparse address spaces. The other thing is there's a scheme with a inverted page table architecture. And this is utilized by the 64-bit UltraSpark and PowerPC because it has hardware support for this. And here we have the illogical address is the PID, the page, and the offset. And then that maps to a physical address. So you're actually looking at this from a different perspective. You are actually searching by the process and the page, not to come up with your physical address. So this is the inverted page table architecture. Other than those two examples, I haven't seen, and the UltraSpark and the PowerPC, especially the UltraSpark, are not too heavily used, and so I don't see this in too many other places. But this is just another approach. So that concludes the presentation on main memory. So we are on to chapter 9, I believe. Yes, which is virtual memory. So how many of you have heard about virtual memory and have any experience with virtual memory? So Daniel Jones said, isn't that like swap space? It is very much, because you are storing things into onto a hard disk. You're swapping it out generally into a hard disk. And the key thing here is it gives the appearance of a larger memory than actually exists. Let's see. There we go. Oh, wrong presentation. That's the administrative slides. Let's try that again. It keeps doing that. Sorry, doing a little bit of meeting manager. Here we go. Is that it? I got too many presentations up. I guess I gotta start closing down some presentations. Sorry for that. Okay, there we go. Okay, now you should see the virtual memory presentation. So let's go ahead and get started. So just the usual overview. We're going to describe the benefits of a virtual memory system, explain the concept of demand paging, which we talked about a little bit in the main memory section, but the big benefits of paging come in play with virtual memory, and then discuss various principles of working set models and examine the relationship between shared memory and memory map files. So that's another topic that's may be of interest to you, and then explain how kernel memory is managed. Actually, I'm not sure we'll get to that. We probably won't discuss so much about kernel memory. I think I omitted that as we went to this online format. So the justification, let's see. Sorry, remembering where I'm at. So the justification for virtual memory is the code needs to be in memory to execute, but the entire program is rarely used. So error code or unusual routines typically won't be loaded unless those things happen. And actually, your application may exist in a certain part of the program for extended periods of time. So that would be the only areas that would be in there all the time. And certainly the memory space, parts of it can be swapped out without a problem because you're working in particular areas. You can think of the way you code. You might be in a loop, or you may be using certain methods over and over again for a period of time and not really using anywhere else. So this takes advantage of that is virtual memory. So again, like I said, entire program doesn't need to be loaded at the same time. And so we are considering the ability to actually partially loaded programs. So the program is no longer constrained by the limits of physical memory. So you can actually have a program run that requires more memory than you physically have available by swapping in and out pages on demand when necessary. Each program takes less memory while running if you have some of it swapped out. So therefore, you can utilize the CPU better by allowing the context switch time to be lessened with processes coming in and out of the CPU, that you are swapping in and out less memory information because you are basically working with pages on demand for each of the processes. So you can have more than one process swapping in and out and still maintaining some of their content or their memory usage in the main memory. So and then that last bullet is basically what I was talking about in terms of context switching. You need less I/O to swap in and out processors, and so programs can run much faster through the utilization of virtual memory techniques. So those of you prepping for the quiz, make sure you understand each of these bullet points for what basically this is a description not only of justification for virtual memory, but what goals it's trying to accomplish. So make sure you understand this particular slide. So virtual memory, it's a separation of the user logical memory from physical memory. Again, taking advantage that only a part of the program needs to be loaded at the same time at one time for any given process or between processes. And the logical address space can therefore be much larger than the physical address space. And that's, again, a big benefit. We noticed that performance increases, though, when you add more memory. And that is because you don't have to do as much of the virtual memory management. So the address space can be shared by several processes. That's the physical or the logical address space, but generally we're thinking about the physical, that more than one process can share, or a lot more processes can share the same memory when they only have to have a portion of their data in their specific pages that they're using. And it allows for more efficient process creation because when you create a process, you don't have to create all or allocate all the memory needed by that process, only the critical part that's part of the startup process. It's on demand. And then more programs can run concurrently, and the less I/O needed to load or swap processes, which we talked about in the justification section. So this is a little bit of repeat. So the virtual address state is a logical view, starts at 0, is a contiguous, whereas meanwhile the physical memory is organized in page frames, which we saw in the main memory discussion, and the MMU does all the mapping between the logical and the physical. So again, virtual memory is handled in such a way that the programmer and the application code does not need to be aware that virtual memory is happening. The only time that you as a programmer would worry about that is for performance issues. And then virtual memory can be implemented via demand paging or demand segmentation. You remember segmentation takes advantage of how we program in terms of name memory spaces, like heap, stack, those kinds of things, and taking advantage of that. And demand paging is strictly divided up into pages without knowledge of the program. So those are two different approaches that can be taken. So here's just a pictorial diagram of how the logical memory can be much larger. The virtual memory can be much larger than the physical memory. And so this is, and then we do a memory mapping. So we can see here, if you take the size of each of those boxes, you see a much larger virtual memory area. There's a memory map and then physical that maps to physical memory that is smaller. And then we have on the far right, pages being swapped in and out of the disk. So the right represents the disk, that when the particular memory contents is not needed, it can be swapped out to disk. And so this is exactly what Daniel Jones was talking about, is swapping. In particular, I know that Microsoft uses the term swap space, and that's exactly what that is, a space that's set aside for pages to be swapped out to the drive. So usually, we talked about the virtual address space, and usually the design for the logical address space grows down while the heap grows up. So we have this diagram of how the code is at the bottom, data heap, and then the stack. Stack grows down into the free space, and the heap grows up. And there, the big advantage is that no physical memory is needed until the heap or stack grows to need another page, and then on demand, it is allocated another page. So here's an example of how the program can run, and that there's pages that it's going to use, but it's not being used yet. So on demand, the pages are mapped to a frame that then is allocated. And so you map your frames as needed on an as needed basis. And then it allows sparse address spaces where they're left to grow and there be holes in the system, and that they can be dynamically allocated, like, for instance, the linked library, dynamically linked library. System libraries are shared via mapping into virtual address space. So again, the mapping will take care of the situation that multiple processes can use the same dynamically linked library. And then the key thing with a dynamically linked library, as I mentioned before, it has to be reentrant code. So does everyone understand what I mean by reentrant code? I guess I'll go ahead and just chime in. So reentrant code means that there aren't data structures in place that will get stepped on if another process comes in at the same time, or data values, so that they have to either store each process has to store their context data in another spot. But basically it's designed so that as many processes as that are using the dynamic linked library can use the dynamically linked library and not worry about leftover data or data being corrupt by another processes. It's designed specifically with mechanisms in place so that you can rely on that imaging being pristine for every process that is going to be using that dynamically linked library. So that's what we mean by reentrant. That as many processes as one can enter those sections of code without worrying about other processes using it. And then we're talking about forking, so that's the little process creation things, and then shared memory is mapped into the virtual address space, which you would imagine would have to happen again, just like any other virtual address space access, it would have to be mapped. So I talked about this in my description before, but we are basically grabbing frames based on demand of the pages. That all of a sudden we're using a page for the first time that would actually cause the need for the allocation of frame. If it's in there already, then no problem. We don't have to do a swap out and a swap in of memory because it's there and we just use it. So that's referred to as a page fault when it's not in the system already, and otherwise you just access it. So a page fault occurs when you're trying to access a page who does not have a corresponding frame in the memory, and then we have to swap it in and out of the disk. So we talk about the benefits of doing that. We pretty much discussed that We talked about the page is needed, reference to it, invalid reference is abort, not in memory, bring to memory. So again, the invalid reference means you're outside of your logical space. You're trying to step on someone else's memory. We abort and give the appropriate error. And then the not in memory, bring into memory, that's the page fault that I was talking about. And then typically it's a lazy swapper, which means you don't actually swap in memory until it's actually needed. You could have a scheme where you have a look ahead situation where a process would advertise that these are the pages that I will be needing, so I have a preference for it to be loaded if there's space available. But generally, it's a lazy swapper that's on demand. And swapper that deals with pages is a pager. Not that too significant. It's just terminology. So with each page table entry, there's a valid invalid, which means that either that particular page it has a corresponding frame and is in memory, or a I, which is invalid, which says we have a page fault, it's not in memory, we need to load it. So initially, of course, you would actually set them all to I because nothing has been loaded. But as each page is loaded into the system, the MMU would actually then put a valid bit and say it's there, and the MMU would have all the address translation information it needs to handle that. So page table, when some pages are not in memory, you can see here, the ones, here's the logical memory, here's the page table with the number here pointing to the frame. So this is the physical address space. So you can see A is in frame 4, which corresponds to the logical 0. And then we have 6 is C, and 9 is F. And so those are all loaded in there. But some of these other ones like B, D, E, and etc. are only contained on the disk but aren't in physical memory. So that's sort of the nature. They get swapped in and out, and you can have holes, and you have and then you have page faults or not page faults when you access memory, depending what's in physical memory. So here's just a formal slide for page fault, which I've already been using in my descriptions and talked about here. So these are the steps that would happen during a page fault. If there isn't a reference to a page in the a frame in the physical memory, it results in a page fault. The operating systems look at another table to decide if it's logical, is a valid reference or not, or the aborts, or just a frame memory. Then if it is a fault, we need to find a free frame to load that page into. We swap the page in to the disk, from the disk into the physical memory. You would give certainly preferences to open frames that aren't being used, but in the case of when there aren't any frames available, then you have to have an algorithm decide which frames to replace. And then we talked about setting the valid and invalid frames. So you would set the new the page to valid when the new frame is allocated and loaded, and then you restart the instruction that causes the page fault to begin with, because now the page that they access has a frame in physical memory and you're able to proceed. So then you restart the instruction. So these are the steps that would happen during a page fault for a given process. So I again alluded to this already. So if there's a free frame, there's not a problem. You just find an open one and you put it in there. But what if they're all being used? First, how much do you allocate for each frame? So and then which ones do you choose to swap out? the solution, I mean, the algorithm that's being used to figure out which pages to swap out is the page replacement algorithm. There are pros and cons to all of them, but there is a clear winner in page replacements, and that's the least recently used algorithm, and we'll discuss that in more detail. But basically, the frame that hasn't been used for the longest period of time is generally the one that's swapped out. And it is such a popular algorithm that undoubtedly most hardware platforms for computers have support for that LRU algorithm. And so basically the criteria for choosing an algorithm is you want to pick an algorithm that has the minimum number of page faults that best handles your typical applications and their process behavior. And so that's the criteria that you would use. And the same page may be brought into memory and swapped out and brought back into memory several times is certainly a characteristic of virtual memory. So page replacement, one thing is you want to prevent over allocation of memory by modifying page fault service routine to include page replacement. So the page fault routine will handle this, and you try to minimize the amount of memory allocated, so you actually include that in it can often be implemented in the MMU, for instance. And you use a modified or dirty bit to reduce overhead of page transfers, which means that when you're swapping out a frame, so basically swapping page out of a frame, you actually have a bit that says, hey, nothing has changed in this memory that I'm getting ready to swap out. You don't actually have to write it back out to disk. It's the same as the last time it was loaded in from disk. So that is definitely a performance enhancement feature that's, again, generally supported by hardware, is that there is a dirty bit that says that it has been changed since the last time it was read in from the disk. And the page is the logical representation to the physical frames in memory. So there is this separation or indirection that allows the virtual memory space, the logical virtual memory space, to be to be supported on smaller physical memory. So basic page replacement is steps is you find the location of the desired page on the disk, you find a free frame. If there is a free frame, you use it. If there's not a free frame, then you have to invoke your page replacement algorithm, which looks at the dirty bit and does all that things. Basically, you don't have to swap it out with the dirty bit. If it is dirty, then you do have to actually write it back out to the disk. Bring the desired page in the newly free frame, update the page and frame tables. Again, your housekeeping. Continue the process by restarting the instruction that caused the trap, and note that potentially 2 page transfers for page fault can happen, that you are writing out and reading in, which increases the effective access time for the memory. So when you're actually accessing memory, you know if you have a page fault, that is going to have a performance hit on that particular process. And in general, that process will typically get swapped out, or do a context switch out of the CPU when that happens, so that any process that has the pages they want in the physical memory frames will typically get access in a system that allows for preemption. So let's see, just checking my notes. Yeah. So first of all, the one of the simplest is the first in, first out algorithm, and that just says that as frames go in, you keep track of the order that they came in basically a FIFO queue, and when it comes time to replace it, you just said, okay, that's the oldest one. It was first one in. It's the oldest one. When we get a page fault, we're just going to take that one. So here, this is talking about a reference string. So this is saying I'm accessing page 7, and then followed by that, I'm accessing page 0, 1, 2, 0, 3, 0, 4, et cetera, et cetera. Those are the order of the logical pages that we're accessing. And here's an example down below where we have the physical frames, and you can see here as we map across, we have page 7 put into the first frame, and then on the next cycle we have page 0 being put into the next frame, and then 1, and then we have a page fault. So for 2 is not already in the 3 frames that we have. So this is the physical memory, the 3 frames. And so then we have to take 2, and by the FIFO algorithm, the first one in was where logical page 7 is. And so that, which is the very first frame, so 2 would be put there. And as you go across the string of page accesses, you can see the update of the physical frames as we move along. And then you can also see and keep track of where page faults have happened. So you can see here that at, let's see, 1, 2, at 5, basically after that break, when the logical page 2 comes in, that ends up with a page fault. The next one is 0, which also is not in the system. Is that right? Let's see. 7, 0, 1, 2. Anyway, there appears to be a page fault in the next one, but as you go through the algorithm, you can go step by step and look. So 7, 0. Sorry, I'm kind of doing it on the fly here. The 2 gets replaced in page 0. Oh, okay. So this is actually the 0. It's the second 0 access after. Oh no, it's a third one after 3. That's the page fault, and then 4 is a page fault, and then access to 2 is not a page fault because it's already in the system. And you can basically walk through the system looking at what the physical frames look like and when page faults happen. Just a sort of a heads up, please make sure you know this for the quiz about walking through the frames and page faults. I will actually go through an exercise in class that I have put together, but basically I want you to have the ability to walk through an algorithm and see, based on a reference system, what happens to your physical memory and when page faults can happen. One thing to note with this particular algorithm, which is a very simplistic algorithm, is that there is an anomaly called Bellide's anomaly. And that is that it is possible with a FIFO algorithm that you actually get more page faults for a given reference string by adding extra frames, which is counterintuitive, but because you think with extra memory, physical memory, that you should have less page faults. But with the FIFO algorithms and particular reference strings, it is unfortunately possible for the performance to go down with additional memory. So that is definitely a downside of the FIFO algorithm. And here we can see that the way that you track them is simply a FIFO queue that keeps track of pages as they come in, and we'll go through this example in class. I'm going to do this one and one of the other algorithms, but I expect you to understand each of these replacement algorithms unless I state otherwise, and understand how pages get swapped in and out of the frames. So that takes us to the end of our class. Are there any questions about the material or about the class that you've thought of? So like I said, after we go through all these page replacement algorithms, I will bring up an Excel spreadsheet with an example, and we'll kind of go walk through this.
When going over the examples, can you give us an example of this Bradley's anomaly?
The anomaly, I don't currently have an example of it, but I can see if I can come up with one. It is very counterintuitive, so it would be illustrative to see that situation. It'd be interesting to take this reference string and say there's 5 frames and see what happens. I doubt that the number of page frames will go up with this one. And I do know it is possible. I will take a look and see if I can come up with an example where Belady's anomaly comes up. But that is an interesting question. It'd be interesting to run through an example where that actually occurs. So I'll see if I can find one. Any other questions? Yeah.
How does the page fault happen again? Like, can you explain that?
Yeah. Okay. So basically, the page fault happens whenever the logical page is not in physical memory in a frame. So going through this example here that's on this particular side, we can see that initially before this 7 got entered in here, there was nothing. There was no pages in the frames. So this 7 is a page fault. It's saying it's not in there now. I have to load it from disk. Right? I want to access this page. It's not in physical memory. I have to load it from disk. So you can see here the first 3 are automatically 7, 0, and 1. They are page faults because none of those are in memory. When page 2 comes along, there's things in all the frames, but 2 is also not available. But then the next one is page 0, and you can see here it's blank, which represents that the memory is not changing. So here that indicates that that reference to page 0 between the 2 and the 3, that is not a page fault because it's already in memory. It's in the second frame. Can you see that?
Yeah.
So it's already in memory. But then in the next frame, we're accessing 3, and 3 is not in there. So we replace it, and we're replacing it in location 7, and that's because 2 was recently loaded here from the front of the queue. 2 was already replaced. So the next one is the second frame. So you can see that you're good with the FIFO queue. You are going to always pick the one that's been old and they're older. And I'll show you a good bookkeeping scheme to do this as you're walking through this. It's a valuable exercise to walk through this by hand. And in fact, this is a good debugging technique in general, not just for memory management, but as you walk through your program, when you're debugging or programming, this was the technique that was commonly used before debuggers became prevalent. But it's still a valuable technique of actually going through what the program, be the compiler and be the CPU, and walk through the process of what actually happens. It's a great technique for debugging application code as well. But yeah, that's the way it works. Every time you get to a situation where you're accessing a page that's not in a frame, a physical frame, that ends up in a page fault. And then you have to decide if the frames are all full, which one gets removed. And that's the page replacement algorithm.
Okay, thank you.
Yep. Any other questions? Okay, I'm getting ready to stop the recording. So anyway, unless there are any other questions, you are certainly dismissed. Look forward to seeing you on Wednesday. Oh, and by the way, Good Friday is this Friday. We won't have class on Friday.